know that it is a little difficult to be present at 10:30 sharp because it's chill in the air, so of course you might find it a bit difficult to be on time. And even more, I'm going to talk about a little difficult subject in statistics, which is time series analysis. So please have patience. So basically today I'm going to talk over classical time series analysis using R. As you know, this is the workshop which states for the application of R. I am restricting my discussion into two halves. The first half is dealing with some theoretical aspects of time series. Of course, I know because you are from different spectrums, so I think I need to discuss a little more about the theories on time series analysis. And the second half, I think, which will be the post-session half, that will be dealing with the analysis, the time series analysis using R software. Okay. So the pre-lunch session will be of some theories, while the post-lunch session will be of some assignment problem using R. Assignment problem, of course, related to time series using R. Okay, so the first thing is what time series is. Okay, because when I'm talking about time series, so the first question which haunts in your mind, that what time series is. Time series is a bundle of observations which are recorded, which are indexed by time in order. So loosely speaking, you can understand you have a data set which are recorded, which are measured by dint of time points. Okay. So what are the time points? The time points should be equally spaced. That means you have an array of years. So you could not have the years like 1952, 1915, 1920, 2009. No, your time span will be in an increasing manner or in an decreasing manner with some equal space. The spacing should be equally distributed over the entire range. So,
if the spacing is not equal, you will not call it time series?
No, it is a time series, but the analytical part will be a little difficult. So you will have to have some kind of interpolation so that your analysis should be smoother. Okay. You will have to remember one point, that when I am drawing the time series, we have some kind of time frame which are distributed uniformly. The time frame will be distributed uniformly. Loosely speaking, it is a time series data. Okay, but from the analytic aspect, your time frame will be uniformly distributed. Means statistically, there is one distribution is called uniform distribution or rectangular distribution. So your time frame will be of uniform distribution. So unless you get that equally spaced time points, your uniformity, that is an underlying assumption, you might say, your uniformity deflect, and you cannot have the probabilistic or the mathematical perspective of time series analysis. Okay. Well, so as I told you, the time series is a set of observations, each one being recorded at a specific time. Yes. One more thing is the classification of the time series. One is the discrete time series analysis, and another is a continuous time series. Now, discrete time series is one in which the set of time points at which observations are made is a discrete set. That means your times are just some mass points, 1950, 1952, 1954, well, 1955, like that. Okay? But when I am including 1955, that means it is not equally spaced. So again, what I was talking just in just a few minutes before, that your time frame will be equally spaced, because this is the underlying assumption of time series, mathematical time series analysis. So if you are including 1954 I mean, if your sequence is like that, 1950, 1952, 1954, that should be the next number. But suppose in your hand 1953 is there, so then you will have to 1953 and 1955. Then you will have to make an interpolation in at 1954. Otherwise, if you are spacing, that uniformity will not be valid. Means it will be deflected. So discrete time series is like that. That is your in 1950, 1951, like that. And continuous time series are obtained when observations are made continuously over time series intervals. Now, you might ask me that, well, as far as we know, time is like a continuous random variable. Now, how do you classify a continuous random variable and a discrete random variables? Well, there is one thumb rule in the time series analysis. If your time span is of 1 second, then means not more than 1 second, then we will consider that time series observations are continuous. And if your time span, means when I am talking about the year 1952, 1953, so your time span is 1 year. Or 1952 January, 1952 February, your time span is 1 month. So for these type of things, your time series will be considered as discrete time series. So basically, when your time span is exactly 1 second or less than 1 second, then you will say that your time series, the data is of continuous time. And if it is more than 1 second, even if it is a daily data, we will say that your time series is a discrete time series data.
No, that's a subjective definition, right?
That's a subjective definition. Yes, of course, of course. Well, so here are a few time series plots which I am going to show. The first thing is, look at those two smileys. In statistics, no matter what type of time series data you are talking about, you have to join the points. So this is, you see that the time scale is always along with the x-axis, the first thing which you have to dig in your mind. And the second thing is, well, so this is the annual GDP of USA. So suppose I'm talking about the year 1930 and the GDP is like there, and 1940 the GDP runs somewhere here. So you will have to join, okay, the time series graph. This is a time series graph. The time series graph cannot be a bar, but in some of the cases, particularly non-statistical cases, I have seen lot of times people made a mistake of drawing a time series graph in terms of bar or in terms of points, like P's. Please do not do like that, because as per the definition of time series runs, the time series graphs should be of the continuous manner. Means you have to join the points so that you have a line like that. So a discrete time series, it is the, why we will call this as a discrete time series data, because it is a yearly data. You will see, as my colleague said, that of course it is subjective. So it is a discrete data, so and it states the transformation rate of Indian rupee to $1 US. So you will say that at 1975, what was $1? I mean, what is the equivalence between $1 and the amount of Indian rupee? So you will just have some point over there, have some point over there, have some point for 1985, and what you are doing, as I told you beforehand, that you will have to join those points to have these zigzag lines. So these lines, these whole structure is the time series plot. Okay? Yeah.
Just as you said that this is the yearly data.
Yes.
So between 1985 and 1990 there should be 5 points.
Yes.
So how do you get this zigzag?
Yeah, actually, okay. So I have drawn this picture. Actually, it was a quarterly data. Okay, quarterly data means in between 1980 and 1985. So if you have 1981, there are 4 points. Just to make the picture as far as precise and as far as clean, I have written on just the years. Okay, not those quarters, because if you incorporate those quarters like Q1, Q2, Q3, Q4, so you can understand for 5 years, so 20
You
points.
said yearly data, so I thought that just maybe 1 point a year.
No. The originally the data is of quarterly data, so when you are drawing, then this means drawing with the edge of R, then your zigzag will be coming. But when I am saying yearly, that means yearly.
In fact, these data are available on daily basis.
Pardon?
These data are available on daily basis, I think.
Yes, it is of daily basis, but no, I mean I have borrowed this data from US Economics Times, and there it was given in terms of quarter, so Q1, Q2, Q3, Q4 like that. So 20 points actually in the original data there were 20 points.
So quarterly that is your average of the 4 months, right?
Average of 4 months, okay, January, February, March, April. No, it is of 3 months, January, February, March, April, May, quarter.
So it has been already smooth. If there are any fluctuations that has been already smooth.
No.
If you take average, that is smooth.
Yeah, so when I am taking the average, it is smooth, but when you are drawing that, means when you are drawing in between 80 to 85, then there should be for that quarter, there is zigzag.
No,
that's what our question
was.
was.
I am saying that below 3 months, you use all information.
Yeah, below 3 months we have all.
Yeah.
But whenever you are, please,
That means by this definition, most of the real life data they are basically discrete.
Yes. But there is one more which I am going to show, which is taken as a continuous time series. You just think of ECG data, which are measured in microseconds most of the time. So yes, here it is. You will see. You see that these are the voltage and these are the seconds. So within a second, fraction of bits are coming like that. So in ECG data means most of the time, the medical data, they are of continuous. They are considered as of continuous data. Okay. But in economics times or in kind of agricultural time series plot, most of them are taken as discrete, because you know that is in analyzing the discrete data, it is easier as compared with continuous data, because in continuous spectrum you will have to have some sort of distributional paraframe. Okay, yeah, another one more one can think of, that is the stock returns. Stock returns, you will see, of course, this is an yearly data, but you can just you can think of the second, expression of minute or expression of second, that is in every second how the stock is getting returned or not. So you can convert, you have that liberty to convert a discrete data into the continuous spectrum. Okay, and one more thing I think which I have missed earlier to mention, that is a discrete valued time series. That means your value of the variables are discrete. So value of the variables means I am not talking about the time. As you see that along x-axis the time scale is there, okay, no problem. But along y-axis your values of the variables. So if you consider the car accident, so you understand that is 2 car accidents, 3 car accidents, but not 2.7 car accidents, not like that. So this is the time series plot on car accident, but it is a discrete valued time series data. So remember, I am not talking about discrete time series data, but I am talking about discrete valued time series. That means your observations are of discrete nature. Now, as we are discussing, time series plot is the most important part for a layman who does not have any knowledge regarding the time series. Because by a plot, you can summarize and you can have a precise picture over the entire time frame, and you will have to have some idea about forecasting. The most prominent part of time series plot while drawing is of aspect ratio. Now, what is aspect ratio? I think most of you are familiar with photography. In photography or in some kind of structure, there is one point which is called golden ratio. Are you familiar with this term, that golden ratio? Mathematically, there is one definition of golden ratio. It is nothing but, say, A is one number. So A plus 1 by A, that will be 1. That is the definition of golden ratio. So aspect ratio in photography, you will see that sometimes one photo looks good while you are taking in landscape mode, and sometimes one photo looks better in terms of portrait format. So what is that? That is nothing but some kind of metric which is called aspect ratio. So while presenting a time series data, you will have to keep in your mind that aspect ratio is very crucial. How to measure the aspect ratio? Ratio of height to width. So if you have a picture, you have that height, you have that width. So the ratio of height to width, that will give you aspect ratio. And by aspect ratio, your time series plot will be more aptly. Now, mostly in time series plot, our required aspect ratio should be 0.618, and if your data is really longer, that means if your data is consisting of more than 100 observations, then your aspect ratio is expected to be 0.25. Now the good part in R is that you are going to learn R in a while, that in R you can change your aspect ratio. There is one option is called ASP. So if you just say R, ASP is equal to 0.2, it will squeeze your graph as per your aspect ratio 0.2. Or if you will say that, well, please check aspect ratio is 0.61, then R will engulf your graph as per your said aspect ratio. So now you will see the same data series I have drawn using R. This is one and that is another. So what is that data? I presume this is the, this is the river data. River data means this is the water level in the month of, I think, from 90 to 90 river of US, Northern America. So altogether 18 rivers were there. So this is the water level, and these are the months from 1990 to probably 1980. And this river data is an inbuilt data in R. So if you just go through R and just type river, it will give you back the entire data. So that's not a problem. So we will see that aspect ratio I have chosen as 5, and that will give you this type of picture. And aspect ratio I have chosen as 0.2. That is, the picture is looking like that. So it's your turn to say which looks better. Is this or this? What is the difference? If you look at the difference carefully, you will see that the y-axis is little elongated here, while this y-axis is little pressed up, little squeezed up. So of course I will say that for your paper, for your article writing, this type of picture is much catchier as compared with this type of picture, time plot. So in drawing the time plot, aspect ratio, of course, it leads a potent term.
If the second one is more informative, maybe not.
Informative in the sense, it is a good question. Okay, thumbs up on Aditya. Informative in the sense that, see, it ends at around 120, the time point. These are the time points, okay? I am not writing in terms of year, so these are the time point. Okay, so let's 19 is your 0 time point, 1920 is your 20th time point, so on and so forth. So here you will see that it comes as around 125, but here it is more than 125. So basically you will have a better perspective towards the forecasting. Okay, so if you have this data, it will give you a better perspective of prediction. Forecasting means prediction. So if you are really wanted to forecast about the water level of the river in Northern America, say for 1940, then this pattern, this is more elongated. So right from this pattern, you could have a better approximation as compared with this pattern.
Sir, I don't understand. I mean, how can you say that this will give you better forecast? I mean, because you have the same data over same interval, right? So how can you have a better?
No, but this is a squeeze data, no?
Yeah, but
this is a squeeze data.
But the same.
You just pattern. Look at the pattern. The more you have the curves,
yes.
The more you have the curves, better will be your sense of approximation.
I mean, if you want to forecast.
No, forecast means right from the picture. I'm not talking about the mathematical forecasting, but if you have three this type of circle, this type of dome-like shape.
But they are same. If you look at the bottom picture top, they are exactly same. Exactly same. It's not very different.
No. But this is much squid. Squid.
That's a visual thing. I mean, it is no extra information. It's just a visual thing. I mean,
yes, I mean, I'm talking about the visual things. I mean, I'm talking about the forecasting from the visual.
Since you are talking about forecasting, that's my objection.
No. Means you see that is you can see that is from 9 to 11.
Yeah.
That picture looks like that, and it is from 4 to 16.
Oh, that's okay. That's okay. That's a scaling. That's in a broader scale or smaller scale. That's all.
No, but it is like 125.
Yeah, this is also 125.
No, it is around 120 because I think I have drawn this picture and I have taken more of some values here.
You take some extra data, that's different. But
no, these are not extra data. Means just by this, if you have your aspect ratio, in fact, let me give you some details regarding the aspect ratio. So when you are giving your aspect ratio, R will, I mean, I wanted to discuss it later on in the session of in our session, but while you have raised that question, let me finish here that queries. In R, when you are writing aspect ratio, the less the aspect ratio is, your graph will be more extended. Means there is an inbuilt syntax.
That's about visualization. I mean, how well you resolve your data.
Yeah.
That's I understand. But my question is, whenever you are talking about forecasting should be beyond your data interval, right? That's an interpolation.
Yeah. So extrapolation.
Extrapolation.
Yeah. So that's what I understand. But that's what I am trying to say, that in R, while you are giving the lesser aspect ratio, they will give you some extrapolated data, some additional data points beyond your data.
The extrapolation should be same. I mean, if you have the same set of data, whether you plot it with this aspect ratio of 0.6 or aspect ratio of 5,
yeah.
when you extrapolate it numerically, the extrapolation should be same. It cannot be different. Since you are getting the same data.
No, since we are talking about the time series data, they will check the seasonality.
Sorry?
They will check the seasonality.
Seasonality?
Yeah, seasonality. Yes, that's variation.
Yeah.
And aspect ratio 5 means they will understand that the seasonality is bigger.
Yeah, but when
seasonality means the R syntax.
Maybe my question is not clear, but I am trying to say, when you write the output in a data file,
yeah.
so you have all the data points there,
Yes.
Now, whether you visualize it, that with the aspect ratio of 5 or 6, that should not matter in the analysis of the extrapolation.
Yes.
That's my question.
Yes. But extrapolation is not that usual sense of extrapolation here.
I mean, whether you are doing
Means you
linear
just for a
or...
bigger spectrum, you can take that this is an extrapolation. Okay.
So you using some polynomial to extrapolate.
Yes.
Yeah, so that, I mean, if you have the same data and extrapolate using a fixed polynomial, you should get the same result.
That's what I'm trying to clear up. This is not the, I mean, the extrapolation is not from the straightforward polynomials. Because it's time series, actually for this type of data, two polynomials are running. Okay, one is the trained polynomial, another is the seasonal polynomial. So when you are giving the aspect ratio, the seasonal polynomial is extended. Means R is taking the seasonal polynomial is not as same as the seasonal polynomial over here.
But the data is same.
Data is same. That's where the point is. So I wanted to discuss, as I am told earlier, that is I wanted to discuss it beforehand, after in the session of our
yeah, if you change the polynomial, then of course the
yes, because two polynomials, not one polynomial.
But if I give the same set of polynomials in this data set, I should get the same extrapolation.
The trained will be same.
Yeah.
The trained polynomial, whatever you are seeing or whatever we know regarding the extrapolation method, mathematical extrapolation, it is all about the mainframe. Yes, it is all about the mainframe polynomial. But in time series, there are two polynomials.
Trained polynomial, seasonal polynomial.
Season polynomial. Seasonal polynomial is getting changed when you are changing aspect ratio. In brief, that is the thing.
That means your aspect ratio is actually affecting your this
Choice of polynomial.
Yes.
Choice of polynomial.
Yes, yes,
there is
yes.
aspect ratio dependent.
No, so there is another option in R as well. You just let it be done by R, means optimum aspect ratio. That is because then they will check which seasonal polynomial give you better forecast. That's why I have used the word
That's the
forecast.
point we are missing. Because when we write a program, we decide our polynomial. That's
Yeah.
not related to
Because most of the time we didn't write that aspect ratio. We didn't mention because we just let it in the hand of R. Okay, let R decide what would be the aspect ratio.
Okay.
Then you will decide and then you will give the base.
Yeah, the base picture they will.
Okay.
That is the problem.
According to its inbuilt function or
Yes,
whatever it
yes,
is.
yes, yes. Is that clear? Any other question?
What we usually observe from the observational point of view, if there is any feature which is hidden, to change the aspect ratio, it will be observable. If you change the aspect ratio, then those hidden features will be observable.
Yes, those hidden feature, if you change your aspect ratio, those hidden feature will be changed.
But then the result will also change depending on the choice of aspect ratio, right?
Pardon?
Then depending on the aspect ratio, your result will also change, right?
Yes.
So then how do I?
But I would say that is result means the forecasting figure might be changed, but it is very insignificant. That's how they figure out the optimum. Means it is of order 10 to the power minus 3, 10 to the power minus 2, but it will be changed significantly in the context of picture.
Picture is
No,
okay.
then I think that will be with how significantly that will change will depend upon the variation of your data points. If your data points
No,
are widely
no,
separated,
that
then the variation may be huge.
Now what he is saying that the R is going to decide the polynomial based on the aspect ratio that is.
Yes, that is means
That is her point.
No, what
if you are not mentioning any aspect ratio, then the polynomial chosen is done by R.
No, what I am saying is suppose here in your this graph says the variation of data point is very less. But suppose I have a set of data point where the
Huge
variation-
data point you mean to
Yeah,
say.
means the variation is huge. Means my
The span of the data you meant to say,
data
yeah.
is huge. So in that case, the choice of my aspect ratio, whether it is-
Surprisingly, when you have a span, I mean, surprisingly when you have a huge data set, means the span of the data set is huge, then your aspect ratio, it is just...
I am not saying spend in terms of time, rather I am saying spend in terms of the variation in the data.
The values of the variable.
Yeah.
Okay.
Suppose it's from -50 to say
Value.
-5,
Value.
+500.
Surprisingly, that's what I want to say. That is surprisingly, it won't be changed. Means even if it changes, it is very, very insignificant. It will change. The aspect ratio will give you a change of picture when your data frame is large. Do you understand? That is the year, the span of the year is
That variation.
but the values of the variable, since in seasonality, we are not incorporating the values of the variable directly, so your picture will not have much change. So that's what I mean to say. Is there any other question regarding aspect ratio? Please ask me, because I think aspect ratio is something which we can discuss about. Because most of the time we don't know about aspect ratio, and we present our plot. We present our plot without knowing the aspect ratio, without having any concern about aspect ratio. But I mean, sometimes even if we have some concern about aspect ratio, we just, okay, it looks good, okay, I will stick to this picture. Oh, it looks bad, I won't stick to this picture. But you will have to remember that hiddenly, that's what my colleague said, hiddenly your aspect ratio is changing the seasonal pattern inside your graph as well. So when you are going to have some mathematical calculation, some mathematical analysis from, not from a mathematical analysis from that same data set, your mathematical analysis should match with the picture you are presenting. So it is better to choose an optimum polynomial which gives you the same mathematical analysis as well as the suitable aspect
Can you
ratio.
explain the algorithm? Suppose I give a particular aspect ratio, how the polynomials are chosen based on the aspect ratio. There must be some algorithm.
Yeah, the algorithm is of, basically it is of mean square error. So they are just incorporating one polynomial which is valid for seasonal fluctuations, and they are checking the mean square error, okay?
For the entire interval.
For the entire interval. So the aspect polynomial, let me name it as aspect polynomial, which gives you the minimum mean square error. R will stick to that polynomial.
And also it can predict, when you forecast something, so always know you have some sort of uncertainty in that.
Yes, of course. Forecasting means uncertainty.
The aspect ratio is issues also telling, and you are also explaining.
Yeah.
So if you change the aspect ratios accordingly, if my forecast is changing,
Yeah,
that means that there should be the range of uncertainty also.
No, but that's what I answered, Shudiptadi. If your data set is really larger, then your aspect ratio does not get any potential influence over your values. Even if it gives you some change, that is very, very insignificant.
But it still seems completely to me. But if you have the same set of data set, and if you calculate this mean square error, that should come out with the same.
No, but you are not. You are missing one point, that your seasonal polynomial is changing. Train polynomial is fixed.
You are choosing your polynomial based on the aspect ratio, right? And based on your mean square error.
Yes.
Yeah.
Yes.
So first of all, you have to calculate the mean square error.
First of all, I am giving two polynomials. First one is the trained polynomial,
Okay.
and first
No,
is
okay.
your aspect ratio.
Yeah.
Then according to the aspect ratio,
Mean square error.
no,
No.
according to aspect ratio, it is a kind of iterative process.
No.
Okay.
But my question is, when you set an aspect ratio,
Yeah.
how do you come to a choice of a polynomial? How do you read it? Aspect ratio and then
Okay. The seasonal polynomial
Yeah.
involves aspect ratio as a multiplier. Okay, so it is like seasonal polynomial fs, that is equal to some sort of observational influence is there plus aspect ratio times some another expression. Do you understand?
What that expression?
I completely
Oh,
forgot.
okay.
This is a
No,
jargon
I
expression.
just want to get the, I don't want the details. My question is that if you have the same set of data set,
Yeah.
whether aspect ratio 5 or aspect ratio 2,
Yeah.
and you calculate, say, error, mean
Yeah.
square error, and base your choice of on that.
Yeah. And then your mean square error is this.
Yeah.
But that proportion, I told you that this is just an addition of two terms. The first addition, the first term remains constant.
But my question is are interpolating based on the aspect ratio inside that interval?
Yes, that interpolation of that seasonal component.
That's what I'm asking. That
And
maybe
I
with
just
a higher
let me write
aspect ratio,
it.
you are interpolating at
Let me write
a
it. That is like, this is a seasonal polynomial. So I just write it like that. These are the observations. So some sort is coming from the observations. And this is aspect ratio times F2. The seasonality for those points, Sx1, Sx2, like that, okay? So now you understand that as per this aspect ratio, these points are interpolated.
Okay, maybe we will learn this during the tutorial.
Okay, you understand this? You are just fixing this. So what about this value? Now once you have, once you are fine, you are happy with your Fs, then your MSE or SSE. Okay, but there is one trend. Okay, let me write it as extra T. So trend equation remains same no matter what your aspect ratio is. So if you choose that aspect ratio is very small or your observations are quite big, then these expressions will not give you significant change in the context of prediction or whatsoever.
But if data points are very less, then this will affect high.
This will affect. This will affect not in the picture but in the forecasting, but in the prediction.
And if I don't say anything about the aspect ratio, what is the default requirement?
R generally choose 0.625 for observation less than 50, and for observation bigger than 50 it choose I think 0.2, 0.05, like very small, so that the contribution due to aspect ratio is getting lesser. Any other questions? Okay. So Vishwadita, you know that is I never thought about aspect ratio in such a broad spectrum. So thank you. It is my privilege to discuss. Because I have just read while teaching in my class that these are the things. But okay, and I'm really happy to have this kind of interaction. Well, so from the time series plot, there is one more point which you can talk about, that is the stability of time series. Stability of time series, and which is in other words is called the stationarity. Stability of time series means usually the mean variance or covariance of time series do not change over time. So I mean I'm not going to the mathematical details because here are some persons who are not from the mathematical background. So better to be concentrated towards these three pictures. There are three pictures you can see. So what are the significant difference you can see right from these three pictures? This picture you will see that mean is increasing. How to check out your mean? This is your time frame. This is your frame of the observation. So your mean is changing, means you will see that the x is increasing out. So for the first picture, mean is changing, while for the second one, mean is not changing significantly, because you will see that is if you stick to the mean is the central value. So for that card, the central value lies somewhere here, somewhere there. So mean constantly lies on almost on a straight line, but the cycle, the pattern of the cycle is getting changed. So you can understand the span. The span of the values are getting changed. So here you can understand that this is the variance. Variance is not a constant. Variance means a measure of dispersion. Dispersion of the data set is getting varied. And while for the third picture, it is a little amusing to see mean almost runs along a line, but there are few cars which are squeezed in between themselves. So these two distance, just look at these two cars. So these two distances are very, very thin, while for this curve and for that curve, the distance means the upper observation and the lower observations, they are little wide apart. So basically their covariability, the interrelationship between the data points are changing over the time. So these three graphs will say that is there are few few instances where you will find mean is changing, dispersion means the measure of scatterness is changing, as well as measure of inter-association, measure of correlation, measure of covariance is also changing. So these are not the picture of stable time series plot. So if you have a time series plot looks like any of them, then you cannot say that your time series is stable. Now what is the problem of being unstable time series? You see, when a time series is unstable, you cannot do some sort of mathematical derivation. So to have some mathematical exposition, you will have to have a stable or stationary time series. Otherwise, you will have to convert your stationary time, non-stationary time series to a stationary time series. Otherwise, you cannot frame any mathematical formulation. Why? Because it is quite understandable that for this span, your mathematical form is different from the mathematical form for this point, from the mathematical from this point. So every time, in every time span, your mathematical exposition is getting changed. So you don't have an unanimous mathematical spectrum over the entire time reference frame. So of course, stationarity is a must condition for time series analysis. So
the middle one has the larger variability.
No, not larger. Variability is not constant. It is getting changed over time. Variability is not constant. How to check that variability is not constant? Means not same. You just look at this span. One is very small, another is little bigger. As compared with these dome, what about this dome? The lowest point lies here and the highest point lies up there. So it is, the variability is larger, getting larger. So variability for this dome is not same as variability of this dome. Okay, so the variability is not a constant or something. Yeah. So for stable time series, you will have to have mean constant here. You see, mean variance and covariance all will be constant over the time. Otherwise, you cannot frame an unanimous mathematical equations. So the question is, how are you ensure that is your time series plot is stationary or stable? Okay, I am ready for any mathematical exposition. If your graph looks like this, you see, that is dome, the variability remains same, mean runs across the line, and the inter-dome distance remains same. For inter-dome distance between 1 and 2 and 2 and 3 are almost same. So the covariability is almost same. So this is a clear-cut picture of a stationary time series. So in data set, means in a real-life data set, this is a clear-cut picture of stationary time series. So I don't know, probably in physics you might encounter with one word which is called white noise or random shocks. I'm not sure if you are this. So random shocks or white noises look like this. So you see that lot of zigzags are there, and more or less the mean of each zigzag runs along a straight line. Okay, so this is a stationary time series. And one more thing, if you are really inquisitive in time series analysis, there is some kind of mathematical checking rule as well, and I have I have found that this is called augmented decay Fuller test. Means mathematically you could also check while your time series is a stationary series or not. So this is augmented decay Fuller test. So I just, for my curiosity, I figured it out that augmented decay Fuller value is -6 here and -2 here. So the more the negative value is, better will be the evidence for the stationarity.
This covariability is not poor.
Pardon?
Covariability is not poor. Yes. Because in ECG, electrocardiogram, if you see this type of data, in that case, covariance, of course, the middle part. Covariance is not the proper, but the side
Covariance
part.
of the middle part means? I mean,
Because some carbon are more closer. Okay. Okay.
here, more or less covariability sustains same.
But if you
But
see the
here,
ECG curve,
ECG curve here.
then it's of course a problem. Electrocardiogram.
Yes.
Then it's of course a problem.
Of course, a problem of what type?
Because the heartbeat should be symmetric
Yeah,
and proper.
in symmetric pattern. But if your heartbeat is not in symmetric pattern, then you can say that is non-stationary, non-stable. We'll say that it is an unstable
In that
electrocardiogram.
case, this covariance still poor there.
This covariance, this concept of covariability stands more there. Yeah. There are a lot more things. If you are really, means we are talking about a discrete, generally on a discrete time series data. For continuous time series data, I have already discussed that ECG curve is an example of continuous time series. So in continuous time frame, there is a little modifications over the discrete setup. Okay, so and this is the non-stationary time series. You will see that is there is a sharp dip here, somewhere here, and again the curve runs up. So this is a particular picture of non-stationary time series. So there are two different approaches. Any questions so far? Means I have long way to go because I know there is, we need a little knowledge regarding time series before we jump into the course of our session. Okay, so if you have any question, I am really happy to accommodate your question. So there are two different approaches of explanation of time series. So you have a time series data, first you plot it and you are make sure about the stationarity or non-stationarity of your time series data. Now we are thinking of building some model. Why model building is necessary? Because one more question is flickering in our mind, that is forecasting or that is prediction. Of course, that is one point of time series data, time series analysis. So there are two types of approach. One is the classical approach and another is stochastic process or probabilistic approach. So nowadays generally probabilistic approach is much out of the shoot, but let us start with the traditional approach or classical approach because it is easy to understand, and I personally believe that probabilistic approach is, I'm not saying that this probabilistic approach is better than the traditional approach, because it is nothing but the old wines in new bottles. So yes, the first and foremost which you will keep in your mind that any time series point, so yt, it has 4 components. I have already introduced you with that word trained and with that word seasonal. So basically there are 4 types of component. One is trained, another is seasonal, another is cyclical, and the fourth one is irregular. Okay, so 4 component together, join together and make one time series point.
In case of this cyclical, please go to the.
Yeah. I'm going for that example.
Train, seasonal, and
Cyclical and irregular.
you can see from the data. But what about the cyclical? If the periodicity of the cyclical pattern is bigger than the.
It is also very much interesting. to distinguish between seasonality and cyclical component.
Also the irregular thing also
Yes,
hard
yes.
to model.
We are going to discuss everything this, so nothing to be worried of. Okay. Trained component, as you, trained. So most of the time you might ask your daughter, Rishti, what is the trend of your dress? Okay, this is the fashion. Oh, mummy, this is the fashion of wearing a flaring skirt. So trend means what is the fashion, what is the underlying trend, what is the pattern of the time series. So for trend, you will have to have a long time series, and you have to approximate your time series by a line, or by something non-linear. So without, it will be a smooth, regular, long-term movement. Okay, so trend is like that. And of course, for studying trend, you will have to study several years, because by 1 or 2 years you cannot predict the trend, you cannot predict the fashion of the time series. And trend is like that, your time points are like that, these are the time points. You see the time points are zigzag, zigzag, peaks and troughs, crest and troughs, peaks and troughs like that, but your trend line is just a smoothing, the approximation of this thing. Okay, this is the trend. So trend is basically the mean. If you just think about the mean of each cycle, this is one cycle, so you just take the mean. Join those mean point, and you will give one line, and that is your trend line. Now the cyclical component, cyclical component is some sort of periodic movement which spans from 2 years, means more than 1 year. Okay, you will see that it is some repetitive movement cycle. The graph is going up, the graph is going down, the graph is going up and down. So that repetitive movement which has the uniform period and the equal amplitude is called the cycle of the time series. And we will say that the time series has a cyclical component hidden inside it. Now the question is, okay, let me go to the seasonal component, because then you will understand that what seasonal component is and what cyclical component is. Seasonal component is, this is also another periodic fluctuations, but the period is less than 1 year. So in time series analysis, a periodic movement is impertinent, okay, but period might be less than 1 year, period might be greater than 1 year. So if your period is greater than 1 year, we will say cyclical component, and if your period less than 1 year, we will say seasonal component. Let's take one example. What do you think? When the puja is round the corner, the sales of dress materials is shorter. So that means every year that phenomena is repetitive. Every year during puja, you will go to the shop, you will buy some new clothes, and you just come back home. So every year during October, September, you will have that boom of buying clothes. So that is the seasonal component present in the time series. While cyclical component is not so easy to understand, because in cyclical component the period is greater than 1 year. Seasonal component is very easy to understand. Okay, during Christmas we always rush to Monginis or sugar and spice, and we try to grab cakes, pastries, muffins like that. So every year you follow that trend. So this is the seasonal component. But for cyclical component, I am going to show you. Okay. Well, I think irregular component comes before that example of cyclical component. Let me quickly go through that irregular component, and then I'll be going for this example of cyclical component, because I have a number of good examples regarding cyclical component. So irregular component is something which is unsystematic, means which is not random, residual fluctuations and unexplained. So okay, I don't want to go for those jargon words because these jargon words might make you tired. Let us have one example of irregular components. আপনারা ব্ল্যাক মার্কেটে কেরোসিন তেল কিনতে হচ্ছে, ব্ল্যাক মার্কেটে চালের দাম বেড়ে গেছে, এই কথাটার সঙ্গে পরিচিত নিশ্চয়ই ব্ল্যাক মার্কেট। Everyone is Bengali here? So you are not Bengali, I see. Yeah. Are you familiar with this word black market?
Just listen.
Means not from the open market. Kerosene oil is not available in open market. So during
Kala Bazari.
Kala Bazari, yeah, thank you. So if you look at the sales of rice over years from 1920 to say 1980, then you will see, and Amurta Sen in his book also pointed it out, that is during the period of Second World War, the sales of the price of the rice got shot up. Okay, means there is one pattern of the rice, say pattern of the rice price. ধানের দাম হচ্ছে আমরা জানি 20 টাকা 25 টাকা 20 টাকা 25 টাকা, কিন্তু 1942-43 সালে আমরা দেখলাম ধানের দামটা বেড়ে গেল বা কেরোসিনের দাম বেড়ে গেল। Why? Because the war was on during the Second World War, I mean to say. So those years, those are the outliers, those are the outlying observation in the time series of sales of rice. So those outliers, those outlying observations are named as irregular component. So irregular component is non-repetitive. Unlike seasonal component, irregular component cannot come year-wise. Okay, it might happen due to some natural calamities, due to some man-made calamities like Union strike or war. But irregular component is purely random. It does not have any precedence. So that's what irregular component is. So sometimes your time series might experience irregular components during the span of the time series. Okay. So these are the notation. YT is your time series, TT secular trained or secular trained, all the same, like Saran, Ishika, or you might say Saran. ST is seasonality, CT cyclical component, IT is the irregular component. Now, mathematically a time series, T means Tth time point. So Y 1952 means it is the observation at the year 52. So YT is a function of TT, ST, CT and IT. Now it's up to you what to choose as your function. In classical model, the function is simple additive. We are going to show it later on. And either simple additive or simple multiplicative.
Secular trend, would you like to repeat once again?
Secular trend and trend are the same. Just I told you, Saran, Ishika, I am Saran, Ishika, but some people prefer to ask me by the name Saran.
YT stands for?
T is the time.
Why?
YT is the observed time series. So it is like price of rice at Tth time point. So of course T might be 1952. This is the year. T might be another year, 2010. So why 2010? What is the price of the rice in the year of 2010? So that is your observed. What you are seeing, what you are experiencing.
So if you don't have a data for a year, then how can you determine this term? So you are saying all this in terms of year. This period if it's over a year, then it is cyclic, this kind of thing. So if my data is
He's saying if there is missing data.
not making data, the data length is very small.
The same question what I asked. If the time period of the cycle is basically larger than your data interval, how can you incorporate the cyclic part in your data?
I'm about to come. Cyclic part is not so easy to interpret.
Another thing, what I feel that because you are showing a time series which can be easily Fourier transform, right? So Fourier transform
Yes,
represent any whether stationary or non-stationary doesn't matter.
Yeah, actually stochastic modeling of time series. I told you.
You can have many cyclical components.
Yes.
So which one to take or which one to ignore? How
Yeah,
do you decide?
it is called the periodogram analysis of time, so spectral analysis of time
The
series.
frequency domain.
Yeah, but I am really sorry. I think discussing spectral analysis here, it is beyond my scope.
That I understand. But since we are talking about only one cyclical component, and
No,
that-
I'm yet to come to the
Oh, I see.
field of cyclical component, okay? I'm just saying that is seasonality might be there, and I think all of you understand what seasonality is, and cyclical component is not so easy to grab. I'm going to refer a couple of examples for that cyclical component, and then we will discuss it in terms. Okay, I will be really happy if you just turn off your phone. I'm sorry. Okay. Okay, I just want to have that seasonal variations. There are some examples, and of course you will dig into your mind that seasonal variation is not longer than 1 year. So there are few examples of sales of departmental stores. Okay, this is a very amusing example of seasonal seasonality or seasonal fluctuation of time series data. It is the quarterly sales of ice cream. Okay, quarterly sales of ice cream, and you see there are 4 quarters, 1, 2, 3, 4. As we know that each year comprises 4 quarters. Okay, 1, 2, 3, 4, 1, 2, 3, 4. So you will see every year, what did you expect? During that April, May, June, July, we just rush for grabbing a cone of ice cream. So that ice cream sales is getting up when in between the second quarter and third quarter. What is meant by the second quarter? January, February, March, first quarter. April, May, June, that is your second quarter. July, August, September. So from April to September, we have some hankering over some ice creams. So you will see that there is one peak. And again, as the winter creeps in, the hankering for ice cream cone is getting depleted. So your car, the sales is getting tapering down. Okay, so this is just like the thing. You will see the trend line is like that. It is little upward. Trend means the mean line. How to calculate the mean line? You have that observation. What is the mean of? What is the central value? The central value is somewhere here. Central value is somewhere here. So central value, do you understand what is meant by central value? This plus this plus this plus this plus this divided by 1, 2, 3, 4, 5. Or divided by 4. Okay, 4 quarters divided by 4. So that will give you mean value or central value. So this is your trend.
What is the reason? Why not just points? Because 2 types of points is there.
What?
One is blue and one is magenta.
Okay. What is, these are the observed and these are the fitted. Okay, fitted means again we have already discussed that seasonal polynomial, you have to have some seasonal polynomial. Polynomial is a deterministic expression, is it? It might not match with the observed. Okay.
So it is fitted.
It is fitted. So here you see that this is the trend line, and this is the seasonality. Means seasonality is like that. Seasonality. And there is one more word, perhaps you might have noticed it, that is noise. Noise is sometimes your fitted observation is little too far from your observed, then I will say that this is an outline observation, okay? Outline. In this case, you will see that fitted exactly matches with the observed, okay? So no outlier observations. But in this case, there is a little difference, so this is kind of noise or outline observation or random irregular component. Just now we have discussed irregular component. Okay. Well, all of you were really curious to know about the cyclical component or cyclical variation. Here is the concept of cyclical variation. As I told you, the cyclical variation is means period of the cyclical variation is greater than 2 years. Now think about the world economy. I don't know how much you are familiar with the spectrum of world economy. World economy goes through 4 types of phases, and that is called business cycle. Okay? Any kind of business. In fact, if you can just squeeze off your world economical spectrum into some business spectrum, there are 4 types of phases, and those phases are not occurred in every year. Rather, they occur over the years. It is a gradual change of phases. This is the recovery, the first phase, recovery of business, then prosperity. So that means your business is getting towards the boom, getting towards the highest peak, and after attaining the peak, do not think you will sustain your peak for infinite time, forever. You must have experienced a recession, so that means you are again dwindling down, and you have to attain the lowest, the most pathetic condition of your business, and that is called the depression. And right from the depression, again you will be coming towards the peak by prosperity, by the aegis of prosperity as well. Now this is called the business cycle. Generally, business cycle occurs in cycle. Okay? So unlike seasonal component, business cycle does not occur over years. Rather, it occurs for in 10 years, 5 years, like that. Okay? It is not fixed. In business cycle, the period of from recovery to depression, the period of this peak to that peak is not fixed. So that is called the cyclical component or cyclical concept. One amusing fact is mentioned in the, I think all of you are aware of recession, world economic recession. So recession is a part of cyclical component. Okay, so it is fascinating to see. Also, I have borrowed this idea from again US Economics Times, that is from 1945 to 2009, US economy experienced more or less 11 business cycles, more or less 11 economic cycles, each spanning over 5 and 6, means not exactly 5, a little over 5 years and a bit lesser from 6 years. This is one example. Okay, I think please.
Tea break.
Yes, tea break. Okay. Can I go for the tea break? I think it's just one hour. Don't you?
1 hour.
Oh, it's for tea break.
আজকে তো আধ ঘন্টা লেটে এসছে সবাই।
No, but they are saying that you have already asked them to be at 10.
10:30 টি ব্রেকের জন্য বলিনি। চলুন
Okay,
টি
no
ব্রেক।
problem, because it's a dry. I know